In Chapter 6, we're going to talk about reaction stoichiometry, the mole quantities associated with chemical reactions. Previously, we've talked about formula stoichiometry, how to go from mass into moles, or number of particles into moles, or molar concentration into moles, for one substance at a time. In this chapter, we're going to extend that concept to thinking about chemical reactions as a recipe that allow us to move from moles of one substance into moles of another. For example, in the reaction representative of the combustion of propane, C3H8, where propane reacts with oxygen to form carbon dioxide and water vapor, a balanced reaction shows us that one molecule of propane can react with 5 molecules of oxygen to produce 3 molecules of carbon dioxide and 4 molecules of water. These coefficients tell us the relative amounts of each substance involved in the reaction, similarly to how a recipe tells us how to prepare something from starting ingredients in order to make final products. This quantity, represented by coefficients in a balanced reaction, tells us both the precise number of all of the reactants necessary to make a certain number of each type of product, and it can tell us the ratio of reactants to products. Therefore, coefficients represent the number of individual molecules, or could represent dozens of molecules, or could represent moles of molecules. And it's this last point, moles of molecules, that's most important to us as chemists, because we often deal with staggeringly large numbers of molecules in a chemical reaction. It's convenient for us to think about a coefficient as representing the number of moles of every compound, molecule, or atom involved in a chemical reaction. Therefore, we can interpret this combustion reaction above as indicative of 1 mole worth of propane reacting with 5 moles worth of oxygen to form 3 moles worth of carbon dioxide and 4 moles worth of water vapor. Figuring out from a given amount of reactants how much product can form, or using a balanced chemical reaction to determine how much of a reactant we need to obtain a certain target amount of products, is reaction stoichiometry and the use of mole quantities to predict reactions' outcomes. So for example, we're going to think about reacting a certain quantity in moles of our reactants and predicting how much product we can produce. Suppose that we react 1 mole worth of propane, C3H8, with 5 moles worth of oxygen, O2. Our balanced chemical reaction tells us to expect 3 moles worth of carbon dioxide and 4 moles worth of water. Like a recipe, if we double a recipe, we expect double the yield in terms of products for a chemical reaction. If I doubled my recipe for the combustion of propane and reacted instead 2 moles worth of propane with 10 moles worth of oxygen, I might expect to produce 6 moles worth of carbon dioxide and 8 moles worth of water vapor. Similarly, cutting a recipe in half halves the amount of product or end result that we can make. If we reacted just a half a mole worth of propane with, say, 2.5 moles worth of oxygen, we might expect to produce only 1.5 moles worth of carbon dioxide and 2 moles worth of water vapor. Ultimately, then, we can say that a balanced reaction's coefficients help us convert from moles of one substance to moles of another. These coefficients will provide us with conversion factors that we can use to move from what we know about one substance in a chemical reaction to what we can expect from another substance in the same chemical reaction. We can use information about what we know, which could include reactants or products, to figure out something about any other reactant or product quantity in a chemical reaction. Suppose, for example, that in this reaction, we want to know how much propane we're going to require to produce 15 moles worth of water vapor. Like other conversion factors that we've done working with moles, we can start by writing out what we know about a starting quantity and look to convert that starting quantity into a target value. Here, we're given that we want 15 moles worth of water vapor produced. And what we would like is to know how many moles worth of propane are required to make that happen. So what we're after is converting moles of water into moles of propane. We set up a conversion factor that gets rid of our starting units, which are moles of water, and converts into moles of our target units, propane. Our conversion factor in this case is going to be built from coefficients of a balanced chemical reaction. This will be the easiest conversion factor that we can build this semester, because all we have to do is look to a balanced reaction to get numbers for this conversion factor. To go from moles of water into moles of propane, we fill in this conversion factor with respective coefficients from the equation above. The coefficient in front of propane, C3H8, is 1. So I'm going to place a 1 here in this conversion factor's numerator. The coefficient in front of water vapor is 4. So I'm going to place a 4 in the denominator of this conversion factor. Therefore, to move from moles of water into moles of C3H8 propane, all I have to do is multiply 15 by 1 over 4. I keep 3 significant figures, and what we end up with as a result is 3.75 moles worth of C3H8. Therefore, we can take any abstract quantity of any component of a chemical reaction and convert moles of it into moles of any other component of our chemical reaction. So balanced equations are used as conversion factors because the coefficients tell us the relative amount of substances involved in reactions in terms of numbers of moles of chemical substances. We can use conversion factors to figure out or predict required amounts of reactants or produced amount of products according to these chemical recipes. Coefficients only tell us amounts, so coefficients will only ever allow us to convert to moles or back. So we can only ever convert from moles of one substance to moles of another substance in a chemical reaction, moles to moles. We can never go directly from mass of one substance to moles of another substance without taking multiple steps. So once more in this chapter, we'll visualize this process with some flow charts that help us figure out how we go from a starting quantity of one substance into a particular quantity of another substance in a chemical reaction. No matter what, we'll always move from moles of one substance into moles of another at some point in this process. And again, our mantra will be, when in doubt, convert to moles, because we can always get from moles of one substance to moles of another using coefficients from a chemical reaction. So, as an example, suppose that we were going into the laboratory to measure a reaction that converts one substance, say substance A, into another substance, say substance B. So, reactant A reacts and transforms into product B. In the laboratory, the most practical means we have of measuring quantities is often mass. Instead of determining numbers of moles directly, we're often given mass as starting information. But in order to convert between quantity of reactant A and quantity of product B, we really need moles. The scheme that will follow when we're given information about mass of substances is to use the molar mass or molecular weight of a material to move from the mass of that material into number of moles. Once we have number of moles of a substance, we can use the coefficients of a balanced chemical reaction to convert from moles of that substance into moles of another substance we might be interested in. Once we have moles of a substance that we're interested in, we can use its molar mass or molecular weight to determine its mass if needed. Let's do a specific example where we have real chemical substances. Suppose that we're synthesizing sodium chloride from the elements sodium and chlorine. In the balanced chemical reaction that represents this synthesis, 2 sodium atoms react with 1 chlorine molecule to form 2 sodium chloride formula units. Or 2 moles worth of sodium react with 1 mole worth of chlorine to form 2 moles worth of sodium chloride. Suppose that we start a reaction with 15 grams worth of chlorine and allow that chlorine to fully react with so much sodium that we'll never have to worry about depleting that sodium. In chemistry parlance, we say that sodium is an excess reactant in that case. We want to be able to predict what mass of sodium chloride will form when we react all of that chlorine out. So, we're starting with mass of chlorine. The best we can do from mass is convert into moles. Remember, when in doubt, convert to moles. It's only once we have moles of chlorine that we can take advantage of our chemical reaction up above. So we're going to have to take a series of 3 conversion steps. One that moves us from given starting mass of chlorine into number of moles of chlorine. Once we have moles of chlorine, we can use our balanced reaction to convert that into number of moles of sodium chloride, the thing that we're interested in here. Given number of moles of sodium chloride, then, we can figure out from its molar mass or molecular weight the mass of sodium chloride produced. So we're going to need a couple of things. We're going to need the molar mass of chlorine and the molar mass of sodium chloride to accomplish this. Chlorine's molar mass is 35.45 times 2, 70.90 grams per mole. Sodium chloride's molar mass is 23 plus 35.45, 58.45 grams per mole. So, let's begin our conversion. We have several steps to work through. Our starting value is 15 grams. 15 grams of chlorine. According to our flow chart up above, the first thing that we need to do is convert grams into moles. So we need to get rid of grams of chlorine and move into moles of chlorine. Once we have moles of chlorine, the next thing we need to do is convert moles of chlorine into moles of another substance, in this case, sodium chloride. Once we have moles of sodium chloride, our final step is to convert moles of NaCl into grams of NaCl. With all of these conversion factors in place, we'll be able to get rid of grams of chlorine, moles of chlorine, moles of NaCl, and be left with just grams of NaCl at the end, the thing that we really wanted to know about. Now we have to fill in these conversion factors. To fill in this one, we need the molar mass of chlorine. 1 mole worth of chlorine has a mass of 70.90 grams. And for the final conversion factor over here, we need the molar mass of sodium chloride. 1 mole worth of sodium chloride has a mass of 58.45 grams. That was the work we did as preliminary tasks, figuring out the molar mass of chlorine and NaCl respectively. For the conversion factor in the middle, though, we can just use coefficients from our balanced chemical equation to fill in directly. The coefficient in front of NaCl up above is 2, and the coefficient in front of chlorine is 1. Thus, we have all of these conversion factors assigned values, and we can move through our calculation directly. 15.0 divided by 70.9, multiplied by 2, multiplied by 58.45. We'll keep 3 significant digits at the end because our starting value has 3 sig figs, and these are exact numbers. Our final result, then, to 3 sig figs should be 24.8 grams worth of NaCl. We can expect to produce this much sodium chloride from reacting fully 15 grams worth of chlorine. Notice that this is not double the mass of chlorine. We started with 15 grams worth of chlorine. We do not produce double the mass of sodium chloride. And that's because masses are not directly comparable for 2 different things. The mass of a chicken egg and the mass of an ostrich egg are significantly different. The mass of a chlorine molecule and the mass of a sodium chloride molecule are significantly different. It's only numbers of moles, or total quantity, that are directly comparable. So let's do a second example. Let's suppose that we want to be pragmatic and only use as much sodium for this reaction as needed, so that we don't have to waste any excess. What mass of sodium would be required to fully react away 15 grams worth of chlorine? See if you can figure this out. Pause this video, then come back for the solution when you're done attempting this problem. So we're going to set this up very similarly to how we set up the first example. We have a starting amount of chlorine in grams, but we can't move directly from grams of chlorine into grams of sodium. We have to first, when in doubt, convert to moles. So we've got to get this grams of chlorine to moles of chlorine somehow. The first thing I'm going to do is divide by the molar mass of chlorine to accomplish that. And then, once I have moles of chlorine, I can move from moles of chlorine into moles of anything else in a balanced chemical reaction. In this case, it's sodium rather than sodium chloride. Lastly, once we have moles of sodium, we can move from moles of Na into grams of Na, given the molar mass of sodium. To fill in these conversion factors, we need a molar mass here. The molar mass of chlorine we determined earlier as 70.90 grams per every 1 mole. To fill in the second conversion factor, we need a balanced reaction. Moles of one substance, sodium, is 2 according to our balanced equation. Moles of the other substance, chlorine, is 1. Lastly, to go from moles back into grams, we need a molar mass once more, this time for just sodium. According to the periodic table, that's 23 grams per mole. We'll get rid of grams of chlorine, moles of sodium, and be left with grams of sodium at the end of this calculation. Once more, we'll keep 3 significant digits, and when we do, we should end up with 9.75 grams worth of Na. For a final example, let's think about how much, in terms of mass, sodium chloride is produced if 15 grams of chlorine are mixed with 15 grams worth of sodium. Here we're given starting amounts of 2 of our reactants. We're going to mix 15 grams of each one together. So, how do we solve this problem? It's like we're given two starting values. We've already figured out what mass of sodium chloride could be produced from 15 grams worth of chlorine. Let me bring that back up. So we showed a few minutes ago that from 15 grams worth of chlorine, we would expect 24.8 grams worth of sodium chloride. What would happen if instead of 15 grams worth of chlorine, we'd reacted 15 grams worth of sodium? What if we used our other starting value instead? 15 grams worth of sodium would have to be converted to grams worth of sodium chloride using the same process as above, except everywhere we see Cl2, we're going to replace with Na. We'll go from grams of Na into moles of Na, from moles of Na into moles of NaCl, and from moles of NaCl into grams of NaCl. And what we end up with will be an alternative solution in grams of NaCl. Our coefficients will be built in as follows. 1 mole of sodium has a molar mass of 23 grams per mole. The coefficient in front of sodium chloride in the reaction is 2. The coefficient in front of Na is 2. Our molar mass of sodium chloride is unchanged. It's still 58.45 grams per mole. When we carry through this calculation and keep 3 significant figures, we end up with a result that shows us 38.1 grams worth of sodium chloride would be produced. So if we reacted 15 grams worth of chlorine, we'd make 24.8 grams worth of NaCl. If we react 15 grams worth of sodium, we'd make 38.1 grams worth of NaCl. So what's the true answer here? Are they both right? How could they both be right? If we mix together 15 grams worth of one ingredient with 15 grams worth of another ingredient, how could we expect to get two different results? Well, they can't both be right. So which one is the correct one? It might stand to reason intuitively for you that the smaller amount is the more correct one. Why is that? The answer has to do with the role of limiting reactants in a chemical reaction. A limiting reactant is a reactant that runs out first. And when it's gone, the reaction can no longer produce any more products. After a limiting reactant has run out, any remaining reactants are considered to be in excess. We saw in a previous demonstration that it only took 9.75 grams worth of sodium to react with 15 grams worth of chlorine. Any more than that 9.75 grams, and sodium starts to act in excess. In other words, there were more moles of sodium than moles of chlorine when we reacted 15 grams of sodium with 15 grams of chlorine. To be able to identify a reactant that's going to be limiting, we need to identify the thing that's present in fewer moles overall. You can watch a demonstration in a video linked in your PowerPoint slides. But what we'll say is that in the last example on the previous slide, chlorine was the limiting reactant because it was present in a smaller relative mole quantity. We can mathematically validate that assumption by calculating what I'll call a limiting reactant ratio. A limiting reactant ratio, this quantity LRR for short, is equal to the number of moles of a reactant divided by its stoichiometric coefficient. In the previous example, 15 grams worth of sodium versus 15 grams worth of chlorine had limiting reactant ratios that look as follows. 15 grams worth of sodium is equivalent to 0.652 moles. To determine that, I just divide by the molar mass of sodium, 23 grams per mole. $15 grams worth of chlorine, meanwhile, divided by its molar mass, 70.9 grams per mole, is worth 0.212 moles of chlorine. It's obvious from these calculations that 15 grams worth of sodium is worth far more sodium atoms than 15 grams worth of chlorine is worth molecules of chlorine. There are many more moles of sodium in 15 grams of it than there are moles of chlorine in 15 grams of Cl2. The limiting reactant ratio for these two quantities looks like this. The limiting reactant ratio, LRR, is the number of moles of a substance divided by the stoichiometric coefficient. In the previous example, the stoichiometric coefficient of sodium was 2. That means that the limiting reactant ratio for sodium is a number that's just a fraction, 0.326. Similarly, a limiting reactant ratio for chlorine is number of moles of it, 0.212, divided by its stoichiometric coefficient. In the previous slide's example, the stoichiometric coefficient in front of chlorine was 1. That's 0.212. Relative to how much of each of these reactants is required to make our recipe run and produce product sodium chloride, we still have chlorine present in a smaller relative amount. The smallest limiting reactant ratio identifies a substance that will run out first. And I'm going to star that substance and keep track of it. When we react 15 grams worth of sodium with 15 grams worth of chlorine, because it's present in the smallest relative amount given by the smaller of these two limiting reactant ratios, is going to deplete first. Once chlorine runs out, there's no more of it to react and produce further products. It's like one of the ingredients in a recipe running out. After that one ingredient has run out, then we can't make any more end result. For a more practical example, suppose that we wanted to make sandwiches, and we have a reaction that converts turkey, cheese, and bread into sandwiches. 3 turkeys and 1 cheese plus 2 slices of bread makes 1 sandwich. And you go into the kitchen to make a sandwich with 18 slices of turkey at your disposal, 5 slices of cheese, and 12 slices of bread. How many sandwiches could you make according to this recipe? And how do you know that? Well, even without looking at the rest of this slide, you likely already intuitively know that you're going to run out of cheese first. And because you need 1 slice of cheese for each sandwich, the most sandwiches that you could make would be 5. That's because relative to the recipe's requirements for turkey, for cheese, and for bread, you have the least relative amount of cheese. If we divide the amount of turkey that you have by the number required for each sandwich or reaction, you get a limiting reactant ratio of 6. If you divide the number of slices of bread that you have by the number required to make each reaction happen, you get a limiting reactant ratio that's 6. And if you divide the number of cheese slices that you have by the number required for each reaction, you get a limiting reaction ratio of 5. We expect cheese to run out first, intuitively and through a mathematical manipulation that could be applied to a chemical reaction. Cheese runs out first. It's the limiting reactant. in this sandwich making reaction. Since cheese runs out first, then what we'll say is that we can always use the quantity of it to predict how much product we're going to make. All we need to focus on is the quantity of a limiting reactant, the thing that we know will run out first, for the purposes of determining how much product we can make from a given chemical reaction. We'll always use just the quantity of a limiting reactant to figure out how much product we can make. In this example, our limiting reactant is cheese. So we go from number of cheese to number of sandwich. Use a conversion factor like coefficients from our balanced reaction. One sandwich requires one slice of cheese. This is a conversion factor, just like the coefficients in a balanced chemical equation are a conversion factor. The result of this calculation gives us what we expect, or a theoretical yield for our reaction. The theoretical yield for a reaction is the amount of product that's predicted by stoichiometric calculations. Whichever of our reactants runs out first will give us a predictable stoichiometric amount or theoretical yield of a product or products. Back in our chlorine and sodium reaction example, because chlorine was present in the smaller relative amount, it had the smaller limiting reactant ratio, it alone is responsible for determining how much sodium chloride product we can make as a result of reaction. And therefore, we can ignore the contribution from sodium in excess entirely. So how do we know if we have to figure out a limiting reactant in the first place? Well, if we're only given information about one reactant or product in a reaction, then we don't have to worry about going through these steps. But anytime that we're given starting information about more than one reactant, we have to figure out which one is limiting, which one runs out first. We can accomplish that by making sure we have a balanced reaction, converting given starting quantities of our reactants to respective mole quantities if needed, figuring out a limiting reactant ratio by taking the number of moles of reactant of each type, divide by its respective coefficient from our balanced equation. We can then use the starting amount of the limiting reactant and the limiting reactant alone to convert to moles of any other component of our reaction. And again, we can only convert moles of one thing to moles of another from a balanced reaction. A flow chart might look like this. We can convert from a mass of limiting reactant, if given one, to moles of a limiting reactant using a molar mass. From moles of our limiting reactant into moles of, say, a product. And, if needed, from moles of a product into mass of a product. Let's do a specific example and determine a theoretical yield. So as an example, let's imagine reacting 50.6 grams worth of magnesium hydroxide with 45 grams worth of hydrochloric acid to produce magnesium chloride and water. What mass of magnesium chloride is expected from this reaction? Because we're given information about two reactants, magnesium hydroxide mass and hydrochloric acid mass, this should signify to us that we're working with a limiting reactant type problem. We're going to need a balanced chemical equation first off. So we react magnesium hydroxide. Magnesium hydroxide has the chemical formula that includes magnesium with a 2+ charge, hydroxide with a 1- charge, MgOH2. Hydrochloric acid is HCl. This reaction produces magnesium chloride, MgCl2, and water. To balance this equation, let's make sure that we have the same number of every atom of each type on both sides of our reaction arrow. We only have one chlorine on the left. We need 2 chlorines, though, to balance with the right-hand side. So I'll put a coefficient of 2 right here. This gives us a total of 1, 2, 3, 4 H's. We only have 2 H's on the right-hand side. So I'll use a coefficient of 2 over on the right-hand side. What I would like to know about is which one of these two reactants will run out first. Which one is limiting? We're given starting masses of these things, so we're going to have to convert these to moles. To do so, we need the molar masses of both of these substances, magnesium hydroxide and hydrochloric acid. The molar mass, or molecular weight, for magnesium hydroxide is equal to 58.32 grams per mole. The molar mass, or molecular weight, for hydrochloric acid is not affected at all by any coefficient that comes up before it. There's just one hydrogen and one chlorine in the formula, 36.46 grams per mole. To convert our starting masses into moles, we need to take 50.6 grams worth of magnesium hydroxide, divide by its molar mass, 58.32. We end up with 0.868. Take this one step further and calculate a limiting reactant ratio. The limiting reactant ratio is the number of moles of magnesium hydroxide, 0.868, divided by magnesium hydroxide's stoichiometric coefficient, 1. Now, do something similar for hydrochloric acid. Convert 45 grams worth of HCl into moles of HCl. Divide by its molar mass, 36.46 grams per mole. We get 1.23. And if we weren't careful, we might incorrectly assume that magnesium hydroxide runs out first. There are fewer moles of magnesium hydroxide, right? But the problem is that for every 1 mole worth of magnesium hydroxide that reacts to make products, 2 moles of hydrochloric acid are required to react. The limiting reactant ratio for hydrochloric acid is the number of moles of HCl, 1.23, divided by its stoichiometric coefficient of 2, which results in a ratio of 0.617. Relatively speaking, hydrochloric acid is actually present in the smaller amount because we require twice as much HCl as we do MgOH2 every time this reaction produces products. Hydrochloric acid is our limiting reactant. It's the thing that runs out first because it's present in the smaller mole quantity. That means that we can completely ignore magnesium hydroxide for the rest of this problem. All we worry about is hydrochloric acid, so I can get rid of this entirely. In fact, now that I know that hydrochloric acid is my limiting reactant, I'm just going to go back to the drawing board and start with information about it. I'm going to convert mass of my limiting reactant, hydrochloric acid, into moles of hydrochloric acid. From there, moles of hydrochloric acid to moles of MgCl2, and then finally from moles of MgCl2 into a mass of MgCl2, because I am indeed asked what mass of magnesium chloride is produced. So let me get rid of the answer here and start tacking on some more conversion factors. To go from what's moles of hydrochloric acid at this point into moles of magnesium chloride, we take advantage of our chemical reaction. Moles of HCl convert to moles of MgCl2 by using coefficients from the reaction above. Coefficient in front of MgCl2 is 1, in front of HCl is 2. Finally, to go from what's now moles of MgCl2 into mass of MgCl2, we need the molar mass of it, which works out to be 95.21 grams per mole. As we move through this calculation, we'll get rid of grams of HCl, moles of HCl, moles of MgCl2, and be left with grams of magnesium chloride at the end. We'll keep 3 significant digits to 3 sig figs. The result should be 58.8 grams worth of magnesium chloride produced as a predicted amount or theoretical yield in this reaction. The sticking point here is that unless we're careful, we could have overlooked that hydrochloric acid was our limiting reactant. We need to take care to make sure that we have a balanced chemical reaction, that we convert quantities of starting materials into moles if they're not explicitly already in moles. And then from starting moles of reactants, calculate a limiting reactant ratio. That's the relative amount of moles, or the ratio of number of moles of reactant to reactant coefficient. Once we have a limiting reactant, we use it and only it to predict the outcome of this reaction. So let's work a few more examples together. Again, I'd encourage you to try these before you watch the solutions to see if you can come up with the right answers. Suppose that we react nitrogen with 3 hydrogen molecules to make 2 ammonia NH3 molecules. If we start this reaction initially with 0.5 moles worth of nitrogen and 0.5 moles worth of hydrogen, which one will run out first? Which is the limiting reactant? And based upon that result, what's the maximum number of moles of ammonia that could be produced from this reaction? Well, here we're given moles explicitly and a balanced reaction too. We can figure out the limiting reactant ratios for our reactants directly. For nitrogen, the limiting reactant ratio takes the number of moles of it, 0.5 moles, divides by its stoichiometric coefficient, 1, a limiting reactant ratio of 0.5. For hydrogen, the limiting reactant ratio takes the starting number of moles of it, again 0.5, divides by its stoichiometric coefficient, 3, for a ratio of 0.17. Therefore, because hydrogen is present in the smaller relative amount, it must run out first. It's our limiting reactant. So, hydrogen is limiting. We can convert from moles of hydrogen into moles of anything else we're interested in the chemical reaction and ignore nitrogen's contribution entirely. So, let's go from moles of hydrogen into the thing that we're interested in, which we can do directly in just one step. That's moles of our product ammonia, NH3. Our moles of hydrogen to start are 0.5. We're going to convert to moles of ammonia by filling in a conversion factor with stoichiometric coefficients. Coefficient in front of ammonia is 2. In front of hydrogen is 3. The result of this calculation, keeping just one significant digit, is 0.3 moles worth of ammonia. So, in a second example, let's react C2H4 ethylene with oxygen to form carbon dioxide and water, another combustion reaction. Suppose that we start this time with 5 grams worth of ethylene, C2H4, and 15 grams worth of oxygen. What's the limiting reactant in this case? And now, what is the maximum mass or theoretical yield of water that could be produced from this reaction? Here we're given a balanced reaction directly, but we are going to have to figure out moles of C2H4 and of O2 from the masses given. Therefore, we're going to need molar masses for both. The molar mass or molecular weight of C2H4 comes from 2 carbons and 4 hydrogens, a value of 28.05 grams per mole. The molar mass of oxygen comes from just 2 oxygens, 32 grams per mole. We need that information to convert given masses into moles. For ethylene, C2H4, our given starting mass is 5 grams. Convert to moles by dividing by the molar mass. We get 0.18 moles worth of it. The limiting reactant ratio is the number of moles, 0.18, divided by the stoichiometric coefficient, 1. Just 0.18 for ethylene. Similarly, for oxygen, O2, we can convert mass, 15 grams given, into number of moles by dividing by its molar mass. This gives us 0.469 moles of O2. For oxygen, the limiting reactant ratio is that number of moles, 0.469, divided by its coefficient, 3. This value is 0.156. From this mathematical workup, it's clear that oxygen is present in the smaller relative amount compared to ethylene. Oxygen runs out first, therefore it is our limiting reactant. So I'm going to start it in the reaction up above. And I don't care any longer about ethylene's quantity because it is an excess reactant. All I need to do at this point is convert my starting quantity of oxygen into mass of water. So we have a means by which to convert mass of O2 into moles of O2. The next thing I need to do is convert moles of O2 into moles of the thing that I'm interested in, water. And finally, moles of water into mass of water. Because we'll need a molar mass or molecular weight for H2O, let's determine that up above. That molar mass comes from 2 hydrogens and 1 oxygen, 18.02 grams per mole. Now we can fill in our incomplete conversion factors below. Our last one, rightmost, uses the molar mass of water. Our central conversion factor that converts moles of O2 to moles of H2O is completed by filling in coefficients. The coefficient in front of H2O is 2. The coefficient in front of O2 is 3 in our balanced equation. Taking care of units, we'll see that grams of O2 go away, as do moles of O2 and moles of H2O. We'll be left with grams of H2O as requested, and as we multiply or divide through and keep 3 significant figures at the end, we should wind up with 5.63 grams worth of H2O. So, suppose that we went into the laboratory and carried out this reaction from example number 2. We react 5 grams worth of ethylene and 15 grams worth of oxygen. But in our reaction, we only produced 4.5 grams worth of water vapor, rather than the 5.63 that we predicted. What happened in our experiment? Did we go wrong somewhere? Or is this an expected result? It's rare that actual reactions or experiments go perfectly according to plan. That's because our ability to make measurements and to carry out reactions thoroughly without making any side products, like in a combustion reaction, soot from incomplete combustion, isn't always possible with perfect precision. When real experiments don't go according to plan or produce as much stoichiometric product as we would have predicted, that's okay and no reason to fear. It's because of our inability to make perfect reactions. As a good gauge for how far off we've strayed in our actual experiment from our theoretical predictions, chemists often produce what's called a percent yield to describe how much we've made compared to what we expected. A percent yield is the ratio of what we actually get from an experiment when we carry it out to what we thought we should have gotten from our calculations, multiplied by 100 to give us a percentage. It's the actual yield divided by the calculated theoretical yield, multiplied by 100. Given the previous problem then, if we actually carry out this combustion reaction and produce just 4.5 grams worth of water vapor, what is the percent yield of water from this reaction? The percent yield is given by an equation, actual divided by theoretical yield, multiplied by 100. In our example here, 4.5 grams worth of water actually produced when we carry out this experiment is the actual yield. And our solution to this problem, the 5.63 grams of water we calculated on the previous set of slides, was our theoretical yield. Therefore, our percent yield is actual 4.5 grams divided by theoretical 5.63 grams times 100. It doesn't matter what units we use for the numerator and denominator in this calculation, so long as they're the same. All we need to do is be consistent with units so that they'll cancel out and just give us a percentage anyway at the end. Here, we're using units of grams for both the numerator and denominator. When we divide 4.5 by 5.63 and multiply by 100, we get precisely 80 to two significant digits. I'll place a decimal point right after the 0 and 80 to keep two sig figs. Therefore, our percent yield for this reaction is 80%, which is actually quite good compared to many other chemical reactions. The remainder of this chapter discusses energy and its use in calculations in chemical reactions. While I would expect you to look at the following slides and at least gain an appreciation for energy as a driving force for chemical reactions, because of our compressed semester, I'm not going to test you on this. I will cover some highlights that you should know about, though. Back at the beginning of the semester, we discussed phase changes and physical transformations from solid to liquid to gas and vice versa. These processes, phase changes, either require heat or release heat as they occur. In a physical change that makes a more diffuse phase, going from solid to liquid to gas, heat is required or absorbed. That process is an endothermic one. The reverse process, coming back down from gas to liquid to solid, condensing phases, releases heat or produces it. And any process that releases or produces heat is exothermic.